Welcome back. Today we'll cover the basics of probability. We'll include both classical and empirical probability, but don't worry a lot about remembering which is which. What's important for statistics is that the ideas that allow us to calculate the probabilities we'll discuss here, the probabilities of an outcome given a known distribution, can be combined, and we will combine them with what we know about other kinds of distributions, specifically the standard normal distribution, the same one that if you standardize a variable that you're looking at z-scores that you're using, can be combined with those to help estimate a wider range of statistical probabilities. Now, if you've ever flipped a coin or played eeny, meeny, miny, moe, you're already familiar with probability. Unless the coin is weighted, for example, you have a 1 in 2 chance or probability of flipping heads, and likewise a 1 in 2, 50% or 0.5 probability of tails. Probabilities can only range between 0, something that cannot happen in any situation, and 1, something that will always happen or is destined to happen, and are usually expressed by statisticians as decimals, 0.2, rather than as fractions, 1/5, or percentages, 20%, though all three are equivalent and you're more likely to hear the last two in popular discussions of probability. Now, a terminology note before we go on. Odds is a technical statistical term that's not equivalent to probability, so it's not correct to say that the odds of getting heads are 1 in 2. For those that are interested, odds are the frequency of an outcome divided by the total frequency of other outcomes rather than the total frequency of all outcomes. So the odds of getting heads on a coin toss are actually 1 to 1, not 1 in 2. The basic quantity of interest here, though, that we're talking about with probability is called relative frequency. That is the frequency of an outcome divided by the total number of outcomes. So, for example, if we wanted to know what slot machines were most likely to win, we could try playing a large number of games at each type of machine and observe how many wins we scored or whether the net winnings were positive at each machine. When we use outcome data like this to estimate probability, it's known as empirical probability. Now, if we actually knew instead how many of each symbol were on the reel, that is, if we knew the sample space of equally likely possible outcomes, we could instead use classical probability theory to estimate the probability of each type of prize. To find the probability of getting a cherry in the first reel, for example, we'd divide the total number of symbols on that reel, counting duplicates each time they occur instead of just once, and we divide by the total number, and we divide the number of cherries by that total number. So pause for a sec. Think about what else we've seen that looks similar to that. The answer is means. If we coded the outcomes we're interested in, cherries, as 1, and every other symbol is 0, then the probability would equal the number of ones, that is the sum of the values, divided by the number of possible outcomes, the number of cases. So really, when we're talking about the probability of an outcome, we could just as easily call it the mean. This is important because means and other statistics related to them, like standard deviations or variance, have important properties we can use to learn more information about a distribution. Now, probability, and of course statistics, can get more complicated in practice. What if we wanted to find out the probability of getting at least one cherry in any position on a single spin? The obvious solution would seem to be adding up the probabilities of getting a cherry on each reel. But imagine there are only 3 symbols, an apple, an orange, and a cherry, each equally likely on each of 3 reels. The mean number of cherries we get could be calculated in the same way, by tripling the mean number of cherries you get on 1, giving us a mean of 1, or 1 in 3 times 3. But we can easily see there are possible spins that won't include a cherry, for example, if we spun 3 apples. Thinking back to the definition of means, this shouldn't be surprising either. In fact, we know from the definition of a mean that the number of possible spins without a cherry will be exactly equal to the total number of cherries that show up in spins with more than one cherry, minus the number of spins with any cherries, that is, the number in excess of 1. Otherwise, it wouldn't average out to a mean. In this case, there are 3 to the third, or 27 possible spins, and 2 to the third, or 8 possible spins without cherries. So while the average number of cherries is 1, that is, we have a mean of 1, the probability of getting at least one cherry is 27 minus 8 over 27. Although the math is more complicated, you'd follow the same basic procedure to figure out, for example, the probability of getting cherries in the first 2 slots, which has a slightly higher reward, typically, than getting one in only the first slot, although you'd have to decide whether to include all spins with cherries in the first 2, or only those where there isn't a cherry in the third, which would give you a different prize. Regardless, the formula is the same. Frequency divided by total number of outcomes, either the number of empirical trials or the size of the theoretical sample space, depending on what you know. The last scenario, trying to find out the probability of getting cherries in the first 2 slots, hints at the idea of conditional probability. That is the probability of an outcome given that we know some other characteristic or outcome that's related, like the probability of getting 3 cherries if you get at least 2. But that's math for another day. Thanks for watching.